All right, welcome to our final exam review for Calc 1, Math 147. First off, we're taking a look at some true-false questions. Now, a few of these are not going to be on the final exam, like number 1 and number 2. I, in the past, had done more review topics from pre-calculus, and those are a couple things that we didn't cover. So you won't see anything like that in the final. This third limit is a trig limit. So remember the two limits that we knew were the limit of sine theta over theta as theta goes to 0. And that equals 1. And then we had the limit of 1 minus cosine theta over theta as theta goes to 0. And that limit was 0. So here the 2x and the x don't match, so we want to multiply by 2 on the bottom and then also on the top. So all we've done was multiply by 1, and then this part here approaches 1, and 2 times 1 is going to be 2. So this one's false. That should actually equal 2. Derivative of the sum is the sum of the derivatives. That is true. Same is true for subtraction. Derivative of the product is not equal to the product of the two derivatives. This should be the derivative of the product there. That's the same thing as fg prime, which is f prime g plus fg prime. So that guy's false. Derivative of tangent x squared is secant squared x squared. Almost. If this was x, derivative of tangent x is secant squared x, but we've got x squared in there, so that's a composition of functions. So it's chain rule. Derivative of the outside function tangent is secant squared at the inside, and then times the derivative of the inside. So that was false. And I'm correcting here the false ones as we go. And let's see, and you guys won't have to do this tomorrow because when you take the final, because it's going to be multiple choice. Let's see, f of x is x squared plus 1. The differential of y, or the differential of this function, is going to be the derivative times dx. So this should be f prime of x times dx. So f prime of x is just 2x times dx. So that 1 right there shouldn't be in there. So this is false. X equal 1, a vertical asymptote here. Well, that bottom factors as x and x. Factors of negative 2 that add up to positive 1. So plus 2 minus 1. So the zeros here are negative 2 and positive 1, so that's true. Vertical asymptotes happen at the 0 for the denominator. If a graph has a cusp at x equal 1, then the limit of f of x as x approaches 1 equals infinity from both sides. That is not true. I mean, if the limit equals infinity, that's going to be an asymptote. Okay, so or it could be, let's see, the limit of f of x goes to infinity. Yeah, this is going to be a vertical asymptote at x equal 1. Okay, but if you've got a cusp, this should be not the limit equals infinity, but f prime at 1 does not exist. That's when you have a cusp. So your graph could look something like this. At 1, you've got a cusp or a point on the graph there. So that one's false. Mean value theorem states for any function f on a closed interval ab, f prime of c is f of b minus f of a over b minus a for some c in the closed interval. Well, there's two things that are wrong here. This is false, the way that it's stated. it can't be any function. Okay, it has to be a continuous function, first of all. Now it is on a closed interval, and we did need that, but then it's for some value c in the open interval ab. And this is saying slope of the tangent equals the slope of the chord, that is the line that joins AF of A and BF of B. Okay, down here we've got this other trig limit. And remember, 1 minus cosine theta over theta goes to 0. So here we've got 1 minus cosine squared 3 theta. Well, remember, 1 minus cosine squared is sine squared. So this is actually the limit as h goes to 0 of sine squared of 3h over 5h. And then we know sine theta over theta that approaches 1. So I want to break this multiplication apart and write this as limit h goes to 0 sine 3 theta, I'm sorry, sine 3h times sine 3h. And then on the bottom I've got a 5 and an h. Okay, so you multiply straight across, so I put the 5 under here and the h under here. Now we want to have these parts match up, so multiply on the bottom and then also on the top by 3. So now these pieces match up, so sine of 3h over h, this piece is going to approach 1. And we've got that 3 out there. So we've got a 3 and a 1, and then as h goes to 0, sine of 3h approaches sine of 3 times 0. Sine of 0 is 0. Okay, this piece is approaching 0. So we've got 0 over 5 times 3 times 1, that's 0. So this guy is true. Integral of tangent is secant squared. That is false. Okay, it's the derivative of tangent that's secant squared. Or another way to write that is if you take the antiderivative of secant squared x, you get tan x plus constant. The integral of the derivative of f gives f back again. So if you differentiate f, you're gonna get f prime. So this much here is f prime of x. And if you do the antiderivative of f prime, you're going to get back to f of x almost, plus a constant. So that was false the way it was. And then the other way, here we've got x, we do an integral and then a derivative. Okay, this one is true. This is fundamental theorem. That's the second part of the fundamental theorem. Almost. I don't want to be too tricky here. I should have done this. I should have changed this variable right here to a t. Because you want the variable of integration to be different than the upper limit of integration, because you want these two variables to match. And then the integral of f divided by g, is that the integral of f divided by integral g? That is false. There's really not a way that you can correct this one. This one is just never true. These are not equal in general. Like, for example, if you look at the integral, just make a real easy example, the integral of 2x over, let's see here, let's do 2 over x squared. No, I'm trying to think of something real easy. Let's do this. X squared over x. There we go. Okay, so if you want to integrate x squared over x, I want to look at that versus the integral of x squared divided by the integral of x and see if these two are the same. So can you integrate the top and bottom separately? Well, the integral of x squared over x, this x would cancel one of those. This is just the integral of x with respect to x, which is going to be x squared over 2 plus a constant. But here, the integral of x squared, that's going to be x cubed over 3 plus a constant. And divide by the integral of x is x squared over 2 plus a constant. So you got two arbitrary constants here. Even if you didn't have those constants, when you inverted and multiplied, you'd have this x cubed over 3 on top. And then invert this and multiply, you'd have 2 over x squared. And this x squared would cancel out all of those except one of the x's, but you have 2x over 3 plus a constant. This would be 2x over 3, 2/3 x plus a constant. Not the same thing as what we had here, x squared over 2, or 1/2 x. So be very careful not to do this when you're evaluating an integral. Don't integrate the top and bottom separately. You'd have to bring your exponent up as a negative and multiply it through, use power rule, or do a u substitution or something like that. Okay, short answer. Symmetry. What symmetry does this graph have? So we talked a little bit about symmetry when we did graphing. So notice here that there's odd exponents. These are both odd exponents. So this should have origin symmetry. So if you plug in negative x for x, you want to see if you get the negative of the equation. So f plug in negative x is going to be negative x quantity cubed minus negative x. And a negative cubed is going to give a negative. So negative of x cubed. Double negative there is going to make a positive plus x. And that's just the same as negative of the original function f of x. So we've got origin symmetry. And that's it. We'd have to have even exponents on x to have y-axis symmetry and even exponents on y to have x-axis symmetry. Distance between distance formula, don't need to do that one. Let's go ahead and review this piecewise graph. This is just piecewise graphing. We worked quite a bit with piecewise graphs when we were doing limits. So here, this is the graph. Y is negative x. If x is less than 1, it's x squared between negative 1 and 2, and it's 3 if x is greater than 2. So notice your cutoffs here are negative 1 and positive 2. So here, look, the change point between the graphs is 0 and 2, so that's out. Here the change point is negative 1 and 2. Okay, that's okay. Negative 1 and 2, negative 1 and 2. So these are possibilities. So now this is y equal negative x if x is less than negative 1. So y equals negative x is the same as negative x plus 0. So that's the line that has y-intercept 0 and slope is negative 1. So if we graph that line, it goes through the origin here, and it has slope negative 1. So if you run 1, you're going to fall 1. So you're going to get this line here. So it's a 45-degree line downsloping, and that's if x is less than negative 1. Okay, so this line is fall 1, run 1, so that's got a slope of negative 1. If you extend it, it will go through the origin. So that one looks okay. This is the same. This one up here, though, it's got the right slope, fall 1, run 1, but if you extend it, its y-intercept is at 1. Okay, so it can't be D. So these two both match up with the first part of the function. What about the x squared? It's y equal x squared if you're between negative 1 and positive 2. Well, remember that x squared is just a parabola here. Looks like that. And we chop it off at negative 1 and positive 2. So let's see here. X squared, if you plug in a negative 1 in here for x, negative 1 squared is positive 1. So this should hit at positive 1 right there. And then out here at x equal 2, if you plug in 2, 2 squared is 4. So it should hit up here at 2, 4. So -1, 1, yes. 2, 4, yes. -1, 1, yes. 2, 4, yes. So the middle part works for both of those. It's y equal 3 if x is strictly greater than 2. Okay. Y equal 3 is just a horizontal line. Slope 0, height 3. This horizontal line is up at 4, so it's not that one. This horizontal line is at height 3. Okay, so that is C. The graph of y equals sine 2x plus 3. This is from the shifting and stretching section that we did at the beginning. So just want to test, short question to try and test that. Remember, y equals sine x has a period of 2 pi, which is a little over 6. It starts out at 0, goes up to height 1, comes down to -1 at 3 pi over 2, and then back up to 0 at 2 pi. So this is at pi. So remember that if we multiply by a number bigger than 1 on the inside, then that compresses it. Okay, so this is a horizontal compression. So it's half as wide. So instead of one cycle in 0 to 2 pi, it's going to do one cycle in 0 to pi. And then the plus 3 is going to be up 3 units. So we want to let's first look for cycle length here. We want something that's a little over 3 units long. So here, this is 6. This does a cycle in 6, so that one's out. So not that one. Here, this does a cycle inside of about 3, so that's a possibility. Here, this is a cycle inside of 6, that's out. Here we've got one cycle in pi units, a little over 3, so 2 possibilities here. So now this takes the sine graph and shifts it up 3. So it's a horizontal compression, but it doesn't shift it left or right. A sine graph starts and then goes up and then comes down lower than where it started. This one starts at x equals 0, goes down to the bottom, and then comes back up to the top. So that's like a cosine graph. And then plus the number out in front here, this is 1 times sine. And remember that multiplier out in front is your vertical stretch. And remember a sine function goes from 0 up to height 1. And the middle of this curve is centered at 3, and it's going up 2 units and down 2 units. So it's got an amplitude of 2 instead of 1, whereas this one's centered at 3, and it goes up 1 and down 1. And 3 is 1, 2, 3 units above 0. So, and this one looks like the sine graph. Okay, starts at 0, goes up, down, and then, so it's got to be this one here. And of course you could graph this on your graphing calculator, and it would probably help you place with these guys. Okay, some short answers with limits here. Of course, if I do this one with a general function though, then it'll be harder to match up. If I give you the graph of the original function and then say what's the graph of the shifted function. So you really do need to know the shifting and stretching. Just go back here just one more time while we're here. Remember this number out in front here, let's call that coefficient A. If that's greater than 1, then it's a vertical stretch, remember? And if it's less than 1, then it's a vertical compression. So if this number was a 2, if it was 2 sine 2x, then it would go up 2 and down 2. And if it was 4, it would go up 4 units, down 4 units from the center. Or here, up 4 and down 4. And then remember, if this number on the inside, if that's less than 1, then it's a stretch. So if this was a 1/2 x, then instead of being pi units wide, it would be, the normal cycle length is 2 pi, it'd be 4 pi units. So that would stretch it out twice as much. And then remember, when you add and subtract numbers inside, that's your left-right shift. So remember that, f, like f plug in x minus 1, this is right 1 unit, so it shifts the graph right. Remember, insides always work as opposites. So adding, subtracting is left-right shift. If it's negative, you go right. Positive, you go left. Inside multiplication is a horizontal stretching or compression. If it's less than 1, you stretch. If it's greater than 1, then you compress. And then the outside, adding, subtracting is up, down. Multiplier in front is your vertical stretch and vertical compression instead of horizontal. Bigger than 1 stretch, less than 1 compression. Okay, so here's our graph of y equal f of x. We want to look at the limit as x approaches negative 1 from the minus. So you're coming into negative 1 here from the negative side. We want to know what's happening to the function values. Well, they're all up here at height 1. Now at negative 1, the function value is not 1, but we're just saying as you get close to negative 1. So this is 1. As x approaches negative 1 from the plus, so as you come into negative 1 from the positive side, here function is going down, getting closer to y equals negative 1. And then, does the two-sided limit exist? If so, find it. No, it does not exist because the one-sided limits are not equal. 1's not equal to negative 1. How about the limit as x approaches positive 1? Here, as you come in close to positive 1, does that exist? Well, yeah, if you go up and over on either side, you're getting close to y equal 1. So, yes, it does exist. Limit equals 1. In 10, if f is f continuous at c equals 1. Okay, so at 1 is the function continuous. So remember, if it's continuous, that means that the function value equals the limit. Well, here the limit equals 1, but the function value is up here at 2. Okay, so no, it's not, because the limit of f of x as x approaches 1 is not equal to f plug in 1. So in other words, 1 is not equal to 2. Limit's not equal to function value. Geometrically, there's a hole in the graph. What's the limit as x goes to infinity? So as x gets bigger and bigger here, your y values are tapering off to 0. Limit as x approaches 3 from the minus side. So as you come into 3 from the negative side, looks like this guy is taking off going up to infinity. And then limit as x approaches negative infinity. So as you go out in the negative direction along the negative x-axis, we're constant at height 1 because this part of the graph extends. So that's 1. Two main interpretations of derivative. Remember that the derivative f prime of x here is the slope of the tangent at x, and is also the instantaneous rate of change. Instantaneous rate of change, ROC, of y with respect to x, WRTX. So that was one of the hour tests. Ask you what the interpretations are. What do derivatives tell us? So geometrically, you could have said slope of the tangent and instantaneous velocity for the two problems it solves. Now here's the graph of f. We want to sketch the graph of the derivative f prime. Okay, so let's line up our y-axis here. Just do a rough sketch. So remember here that the slope of the tangent on y equals f of x is equal to the y value on f prime. That's how we did these. So we sketch our little tangent segments. So like for example, here we've got slope 0. So below that point we're going to have y value 0. Here we've got another slope 0. So down here y value 0. And it looks like that's the only two places that we've got slope 0. Now here, our slope is positive, okay? M is greater than 0. So our y values down here will be greater than 0. But notice that your slope, as you get up closer to the top of the hill, the max point there, that your slope is decreasing. So your slope is positive but decreasing. So that would look like this. And then in between the max point here, the local max there, and the local min right there, which are these two x values, now slope is negative. Okay, this m is negative, goes down from left to right. So this y value is negative, but it's got to come back up to 0 and join up with that one. And then the slopes here after that min point, now they go up from left to right, and they almost approach vertical here. So at x equal 1. So these get positive real quick here, something like that. But then there's no derivative at 1 because there's a cusp on the graph, so you need an open circle. And then on this side of the cusp, to the right of 1, this has a negative slope. Oops, not even a good slope second. Negative slope. Try it one more time. There we go. Negative slope. Okay, so it switches from positive slope to negative slope abruptly on the other side of that cusp. So this is going to go from a positive y value down here to a negative y value. And then the y value stays negative. The slope of these tangent lines are negative, but they're tapering off to get closer and closer to slope 0. So this thing's going to look like this. Going to be asymptotic to y equals 0. So that's x, that's y. That's a rough sketch. Okay, describe the basic geometric idea of the definition of a definite integral. State the definition, tell what it means if you want. So remember that the definite integral gave us area. Okay, this was the integral from a to b of f of x. This definition was this. It was the limit as n goes to infinity of the sum I equal 1 to n of f of xi delta x. And remember, this was just adding up areas of rectangles. So this was a base, this is a height of a rectangle, and this sums up the rectangle areas. Sum the areas. And then this takes more rectangles. And see if the sum of the areas gets closer. Okay, that was basic idea. State the intermediate value theorem. Intermediate means between. This is one of our important theorems. We had Rawls' theorem, intermediate value theorem, mean value theorem. Intermediate value theorem said that if a function f is continuous on a closed interval ab, then for any y that's between f of a and f of b, the function has to hit that y value. So, f of b, there is a value c that's an element of the open interval ab with f of c equals y. Okay, it hits every y value between f of a and f of b. Only continuous functions do that. We use this to show roots, remember. You found one value where the function was positive, one where it was negative, and then it had to hit 0 in between. Okay, here we got implicit derivative. So remember here, y is a function. And let's differentiate this and see which answer we get here. So remember, you start with, let me move this over a little bit here. You start with the two functions here and then differentiate both sides. So we got y squared minus x squared equals 3xy. And then we want to differentiate both sides with respect to x. So the derivative of the left-hand side has got to equal the derivative of the right. So on the left-hand side here, we have, let me give myself a little bit more room here. On the left-hand side, this is a function to a power. So you differentiate y squared, you get 2y, but then times y prime, the derivative of the inside function, and then x squared, that's a regular derivative, 2x, equals, and then over here, 3x times y, that's a product of functions. There's an f, and there's g, and we have to do f prime g plus fg prime. So f prime, derivative of 3x is 3, times g is y, plus f is 3x, and then the derivative of y is y prime. Then we want to bring our y prime terms over on the left and everything else over on the right. So here we'll have 2y, y prime, and this 3x y prime will come over as a negative, minus 3x y prime is going to equal 3y is over here, and bring the negative 2x over as a positive. And then notice we got common factor of y prime. So pull out that common factor. 2y is left here, minus 3x is left here. Right hand side still the same, 3y plus 2x. And now divide off this multiplier. Divide off 2y minus 3x on both sides. And these guys cancel. That just leaves us with y prime. So 3y plus 2x, 2y minus 3x. Alright, hold on a minute. Something fishy's going on here. Oh, 3xy cubed. When I brought this over, I forgot the y cubed. Alright, so let's see, what is that going to do for us? The left-hand side stays the same, so this is all good. On the right-hand side, though, let's see here. On the right-hand side, our derivative is going to change here. F prime is 3, but then g is going to be y cubed, so this needs to be a cube. And then f is 3x, that's okay, but then the derivative of g, the derivative of y cubed, is going to be 3y squared y prime. Okay, so this is going to change to 3y squared y prime. See if we got room to squeeze that in there. 3y squared, and then y prime. So then we bring this term over on the left. 3 times 3 is going to make a 9 right there. And it'll be 9x y squared y prime. So this would be 9x y squared y prime. So then when we factor the y prime out, we'll have the 2y left, but then we're going to have 9xy squared right here where there's a 3x. And then also down here is going to be the 9xy squared, and then also here is going to be 9xy squared. Okay, now 3y plus 2x and 2y minus 9xy squared. Let's see, did I get everything? Oh, 3y cubed. This is 3y cubed. This is 3y cubed. There we go. So 3y cubed plus 2x over 2y minus 9x squared y. There we go. Sorry about that. Helps if you remember that exponent. Alright, now we're up to the problem section here. So first off, we've got some limits. So our first chapter was about limits. So I've given 2 representative limits here, but you want to study the limits on the practice exams also. So these are limits as x goes to infinity. Those are the ones where you can use dominant terms. So in this first one, this is going to be equal to the limit as n approaches infinity. And by dominant terms, this will be square root of 2x squared up on top, and then 5x is the dominant term on the bottom. And now x is approaching plus infinity, so we can just break this apart. Limit, oh, I'm sorry. I wrote an n right there. That should be an x. Limit x approaches infinity. Square root of 2 is 2. And then the square root of x squared is just x, because everything's positive. So that's just going to be x. And then we've got 5x on the bottom. So this is the limit as x goes to infinity of root 2x over 5x. And then the x's cancel, root 2 over 5. And then remember, if the x is approaching negative infinity, then this square root of x squared doesn't give x, but it gives negative x. You get a negative answer. Okay, this second limit, this one is actually equal to the limit as x goes to infinity. Dominant terms again, because we're approaching infinity, are x and x squared. So this is going to be the limit as x approaches infinity. This x will cancel one of those down here. So we're left with 1 over x. And 1 is fixed. Bottom gets bigger and bigger. This is 0. So that's one type of limit. You want to go back and review some of the other types of limits. For example, limits that are formed 0 over 0. So things that looked like the limit as x approaches 1 of x squared minus 3x plus 2 over x minus 1. So notice if you plug 1 in here, you get 1 minus 3 plus 2, which is 0, and 1 minus 1 on the bottom, 0 over 0, which means you've got to do some more work here. Either algebra or looking at one-sided limits, or sometimes multiplying by the conjugate, common denominator, those kinds of things. So here we factor. It says limit as x approaches 1, and on the top here this will be x minus 1, x minus 2 over x minus 1. And the x minus 1's cancel. So now we just got limit of x minus 2 as x approaches 1. And now this is continuous function we can plug in to get the limit. 1 minus 2 is negative 1. Remember, another type of limit is the one that's formed number over 0. Things like this. Limit as x approaches 2 from the negative of x squared, x minus 2, let's see here, no, I don't want x minus 2, say x minus 1 over x minus 2. So notice if you plug 2 in on the top, you get 2 squared is 4 times 2 minus 1, which is 4 times 1, 4. You get a number on top. But on the bottom, 2 minus 2, 0. So this is form number over 0. So that's going to be plus or minus infinity. And we analyze signs. So anything squared is positive. As x gets close to 2, 2 minus 1 will get close to 1. That's positive. And then x minus 2 gets close to 0. X is approaching 2 from the minus side. That means x is less than 2, remember? So if you bring the 2 over as a negative, x minus 2 then will be less than 0. So this is a negative sign on the bottom. Positive over negative, negative infinity. And then if we had things like absolute values or greatest integer functions in there, I can ask you about those things. So you want to study those old exams. For example, limit as x approaches 3, absolute x minus 3 over x minus 3. This is form 0 over 0. Okay, so we have to do some more work. In this case, the more work is one-sided limits. We want to get rid of that absolute value. So let's look at the limit as x approaches 3 from the plus of absolute x minus 3 over x minus 3. And then do the same thing as it approaches from the negative side. Okay, and negative. So we want those two limits. If they agree, that's the value of the limit. If they're not equal, then remember the limit doesn't exist. So x approaches 3 from the plus side, that's x is greater than 3. So if x is greater than 3, then x minus 3 is going to be greater than 0. And then you can just drop the absolute values. So this will equal the limit of x minus 3 over x minus 3 as x approaches 3 from the plus. And that's just 1 over 1, which is 1. However, here, if x approaches 3 from the minus, x is less than 3. And bring the 3 over, x minus 3 is less than 0. So then when you drop the absolute values, you have to do the negative of the inside. So it's going to be limit, x approaches 3 from the minus, and then this will be negative of x minus 3 over x minus 3. So when these guys cancel, it leaves a negative 1 over 1. And these are not equal. Negative 1 is not equal to 1, so this guy does not exist. Now there are a few more things to review in that section. We did squeeze theorem, and we did limits of piecewise functions too. And remember that continuous functions were the ones that we can plug in to get the limit. Those were polynomials and then also rational functions if the denominator was not equal to 0. Okay, next we are finding a derivative, f prime, using the limit definition of derivative. And then find the slope of the tangent to the graph at x equal 3. That's going to be f prime of 3. Shortcuts don't count. So remember here that f prime of x is a limit as h goes to 0 of f plug in x plus h minus f plug in x, and then divide by h if that limit exists. So remember, you want to take and write f of x plus h and try and simplify that as much as possible. So our f of x is x squared plus 2. F plug in x plus h is then going to be, well, whatever x is, it gets squared and then plus 2. And we're plugging in x plus h. So that means we're going to have to FOIL this out. X plus h times x plus h 2 times and plus 2. So first terms are going to give us x squared. Outer terms xh, inner terms another xh, so 2xh, and last terms h squared. And that's all we can do there. So let's go ahead and plug in. So this is going to be a limit as h goes to 0, and x squared plus 2xh plus h squared plus 2, that's our f of x plus h, excuse me, minus our f of x is x squared plus 2, all over h. And then remember that this is going to be form 0 over 0. If we plug h equals 0 in, these terms drop out, and you get x squared plus 2 minus x squared plus 2 over h. And that looks like 0 over 0. So what we need to do is do some algebra here. So remove these parentheses, change the signs. That'll be negative x squared minus 2. So x squared and negative x squared cancel, 2 and negative 2 cancel, and we are left with limit h goes to 0. On the top we've got 2xh plus h squared, and on the bottom we've got h. Still form 0 over 0, but notice we got a common h on the top that we can factor out to cancel what's on the bottom. So this will be the limit as h goes to 0, factor out an h on the top, 2x is left here, plus, if you factor one h out, an h is left here, and then divide by h. So now these cancel, and we've just got left limit 2x plus h as h goes to 0. So this is no longer form 0 over 0, so we can just plug in 0 here. This is going to be 2x plus 0 is the limit, which is 2x. So there's our derivative function, and that makes sense. If we use the derivative rules, we get 2x. And slope of the tangent at x equals 3, so then m tan at x equals 3 is just equal to f prime at 3, and this is f prime at x, so we just plug in 3 for x. So 6 is our tangent. Okay, next we are looking at some derivative rules here. So this first one, I see a quotient rule in there, and then some power rules. And then here I see a product rule. So let's go ahead and rewrite this numerator here. Let me just bring that down here. Let's rewrite that numerator as a fractional exponent. So this is going to be derivative with respect to x. And on the top, that is going to be x squared plus 1 to the 1/2 power, because square root is a 1/2 power, and on the bottom a 2x minus 1 to the 4th. So that's what we're trying to find derivative of. And so this x squared plus 1 to the 1/2 power, that's going to be our f, and 2x minus 1 to the 4th, that's going to be our g. So let's find our f prime and our g prime down here. So f prime, the derivative of x squared plus 1 to the 1/2 power, so 1/2 comes down. Inside function stays the same, x squared plus 1. Decrease your exponent, so 1/2 minus 1, negative 1/2. And then since it's a function to a power, times the derivative of the inside, times 2x. And then these 2's cancel, which is nice. And then our g prime, let's move this over a little. This is a function to a power again, so 4 comes down, inside stays the same, 2x minus 1, decrease your exponent, and then times the derivative of the inside, which is 2. So that's going to be 8 times 2x minus 1 cubed. So then over here we want to do, on the top here, we want to do f prime g minus fg prime, and on the bottom g squared. So here's our f prime. It's going to be x times x squared plus 1 to the 1/2 times our g, which is 2x minus 1 to the 4th, minus our f, which is the top, x squared plus 1 to the 1/2, and then times g prime, which is 8 times 2x minus 1 cubed. And we divide by g squared. The bottom is g, 2x minus 1 to the 4th, and that gets squared. And if you wanted to, in the same step, this 4 times 2, power to a power, you multiply exponents, that'd be 8. And we do not have to do any simplifying here, not for this exam. Okay, let me bring this one down. So I look at this and I see a product of two functions. So here's our f, here's our g. Might want to rewrite here derivative with respect to x of 2x cubed plus 1. And then let's write this as x to the negative 1 power. So times 5 minus x to the negative 1. So here's our f, here's our g. This is a straight product rule. F prime g plus fg prime. So f prime, derivative of 2x cubed is 3x squared. Derivative of 1 is 0 times your g, 5 minus x to the negative 1, plus f is 2x cubed plus 1, and your g prime is derivative of 5 is 0, and then negative 1 comes down times the negative 1 in front is going to be positive 1 times x, and then decrease your exponent by 1, x to the negative 2, and we've got it. Okay, no simplifying needed there. Let me throw in one more example here, something that involves like a chain rule. So for example, let's say we wanted to find, let's say that y equals the tangent of x cubed minus x squared. So this is a f of g of x. And so we want to find the derivative of that. So what would y prime equal? So this is derivative of a composition. And remember, when you do the prime, the derivative of a composition, you do derivative of the outside function. So our y prime is going to be f prime, plug in the inside function, g of x, and then times the derivative of the inside, g prime of x. So derivative of tangent is secant squared. So that's our f prime. Plug in the inside function. So this stays the same, x cubed minus x squared. And now times the derivative of the inside. Okay, well this inside is a function to a power. So this 2 is going to come down in front. Inside function stays the same, x cubed minus x. Decrease your exponent down to 1. But then, since it's function to a power, times the derivative of this smaller inside function. So times 3x squared minus 1. So all of this is the g prime of x derivative of this inside. And this is the derivative of this inside. So, and I would review the other derivative examples from your hour exams and practice tests and/or. And next up, we're doing some graphing with a polynomial here, x to the fourth minus 4x cubed plus 1. So we're doing increase, decrease, concave up, concave down, max, min, and inflection and sketch the graph. So first of all, we need our critical numbers. So we need to find f prime and set it equal to 0. So f prime of x is going to be derivative of x to the fourth is 4x cubed minus derivative 4x cubed is 12x squared, and derivative 1 is 0. So there's our f prime, and we set that equals 0 to find our critical numbers. And then we've got a common 4 and an x squared that we can pull out. So 4x squared factors out. And x is left here, minus 3 would be left here. So either the 4x squared equals 0, and you can divide both sides by 4 and get x squared equals 0, so x has to equal 0, taking square roots, or the x minus 3 equals 0. Add 3 to both sides, x equals 3. So now over here we do our sign chart for f prime. So we've got 0 and 3 as cutoffs, and we pick test numbers here. So let's test negative 1, 1, and 4 into f prime. So we're plugging those here into f prime, or here. Probably easier to plug in here. So negative 1 squared, that's positive. Negative 1 minus 3 is negative. Positive times negative, negative. So f is decreasing. Plug a 1 in. 4 times 1 squared, positive. 1 minus 3 is negative 2. Positive times negative, negative. So decreasing. And then 4. 4 times 4 squared, positive. 4 minus 3, positive. 2 positives make a positive. So increasing. So we're going to have a min here. So f is decreasing from negative infinity to 0 and then also from 0 to 3. So union 0 to 3, which we can put those together, and that's from negative infinity all the way up to 3, it's decreasing. And then increasing is going to be from 3 to infinity. And remember, we close these up because it starts increasing at 3, stops decreasing at 3. And then our min here, the min is going to be the function value at 3, original function value at 3, f of 3. So we're going back to the original function here. So that's 3 to the fourth minus 4 times 3 cubed plus 1. This is 81, and minus 4 times 27 plus 1, that's negative 26. So that's our minimum value. And now we're ready to do some work with f double prime. So second derivative here. Derivative 4x cubed is going to give us 12x squared minus 2 times 12, 24x. Set that equals 0. Got a common factor of 12 and also an x that we can pull out. That leaves an x here. And then a 2 here. So either 12x is equal 0, and divide both sides by 12, x equals 0, or x minus 2 is 0, in which case x equals 2. So now we want to do a sign chart for f double prime. And we've got cutoffs of 0 and 2. I'm trying to line those up with what's above. This is f double prime and f. And let's pick test numbers here. It's going to be -1, 1, and 3. Could have used 4. And we're plugging them in here to f double prime. So -1 times 12 is -12. -1 minus 2, -3. Negative times negative, that's positive. So this is concave up. Plug in a 1. 12 times 1, positive. 1 minus 2, negative. Positive times negative, negative. Concave down. And then plug a 3 in. 12 times 3, 36. 3 minus 2 is 1. Positive times positive is positive. Concave up. So now we look up above and we're going to adjust these. So this is concave up. We look up above, it's decreasing. So decreasing concave up is going to look like this. So it's the left half of that. And then this is concave down. We look up above, it's still decreasing. So that is going to be decreasing concave down like that. Here we're concave up to 3. We are decreasing and concave up. So that's the left half of this guy. So this is decreasing concave up. And then after 3, we're increasing concave up, and that looks like this. So notice that we've got a couple of inflection points here at 0 and then also at 2. We've got inflection. So in inflection points, remember, you have to find the y coordinates. So if x equals 0, we've got to find our y, and that's going back to the original function again. So 0 to the 4th minus 4 times 0 cubed, and then plus 1, which is 1. So that's the point 0, 1. And then if x equals 2, we plug that in. Y is 2 to the 4th minus 4 times 2 cubed, and then plus 1. So 16 minus 4 times 8, 32. So it's -16 plus 1, -15. So that's the point 2, -15. So now we start to sketch our graph, put everything together. Oops, forgot concave up, concave down. So this is concave up from 2 to infinity, and from -infinity to 0. So -infinity to 0. Remember, we don't close these up. Union 2 to infinity. And concave down here between 0 and 2. Okay, now we're ready to sketch a graph here. So we have our minimum point here when x is 3 and y is -26. So 1, 2, 3, and it's going to be down here at -26. Right there. And then we've got 2 inflection points, 0, 1. So 0 left and right, 1 up is going to be about right there. And then 2, -15. So 2 to the right, 15 down, be approximately right there. So this is our min at 3, -26. Got our inflection points here at 2, -15, and 0, 1. So now to the left of 0, we're decreasing concave up. So this guy comes in like this. Between 0 and 2, decreasing concave down. So concavity switches. And then from 2 to 3, we are decreasing concave up. So like this. And now to the right of 3, we are increasing concave up like that. So we get this W, and there's one side that's sagging lower than the other. And of course, always double check this on your calculator. All right, next up we've got a boy who's walking at a rate is a derivative. And he's walking towards a street light that has height 10 feet. How fast is the tip of his shadow moving? Okay, the tip of the shadow, how fast? That's a rate, that's a derivative. So this is a related rate problem because they're asking about rates in here. So let's draw our lamppost here. This is 10 feet. And remember these things with lights and shadows, that's almost always similar triangles. And here's the ground. And the boy is 3 feet tall. So here's the kid, 3 feet tall. And he is walking at a rate of 1 foot per second towards the street light. Okay, so we got this light up here, and he is walking this way at 1 foot per second. And then we want to know how fast is the tip of his shadow moving. So this thing is going to shine down over the top of his head, and the tip of the shadow is right here. Well, as he moves closer to that light, this distance is going to change. But then as he gets closer to the light, like say when he's right here, then the light shines like this. So not only did his distance from the light get shorter, his shadow also got shorter. So this distance out here is changing also. So we want to use two different variables for these quantities here. So why don't we call this one x and this one s. X is going to be the distance from the lamppost, and then s will be the length of the shadow. So they told us they're going towards the lamppost at 1 foot per second. So we know dx dt is equal to -1. And it's negative because x is decreasing. And let's see here. What we want is how fast is the tip of the shadow moving. Okay, well the tip of the shadow, that's going to be the rate of change of this whole side length of the bottom of that triangle. Okay, so we want the derivative with respect to time of x plus s. That's going to tell how fast the tip of the shadow is moving. Now if they asked how fast was the length of the shadow changing, that would just be ds dt. And we want this when he is 5 feet from the lamppost. So this is going to be at x equal 5. So here the derivative of this sum is just the sum of the two derivatives. So this is dx dt at x equal 5 plus ds dt at x equal 5. Well, dx dt, that's given, that's -1. So this is going to equal -1 plus ds dt when x equals 5. Okay, so this -1 is this -1. That's always the same. There's no place to plug in x. So now we have to find ds dt. So we need relationships here in this diagram. And here I see a smaller triangle and I see a larger triangle, and they're similar right triangles here. We're not going to need the length of this side, so we won't need a Pythagorean relationship, but we will need height to base, height to base. So by similar triangles here, we know height to base. Well, actually, it looks like it would be a little bit easier to do base to height. So we know x plus s, the base of the big triangle, over 10 is going to equal base to height for the small triangle, s over 3. And then multiply both sides by 30, multiply by the LCD, or if you want, take cross products here. So this is in, let's see here, this is an S. Let me make sure that looks like an S here. so we don't mistake this for a 5. So this product is going to be 3 times x plus s, and this cross product is going to be 10 times s. So let's multiply this guy in. So we've got 3x plus 3s. And we want ds dt, so why don't we try and solve for s here. This looks like this is not too bad of an equation to solve. So 10s on the right here. And bring the 3s over as a negative, so subtract 3s on both sides. So these guys cancel. We get 3x is equal to 7s. Alright, so let's bring that up here. So 3x is equal to 7s. And let's see, if we divide both sides by 7, we get that s is 3/7 x. So s is 3/7 of x. All the time, s is 3/7 of x. So now we want to know what's ds dt. Well, let's differentiate both sides of this equation with respect to time. So the derivative of s with respect to t, which is ds dt, is going to equal the derivative of 3/7 x with respect to t. Okay, but constants will factor out of derivatives, so this is the same as 3/7 times the derivative of x with respect to t, which is just another way to write dx dt. But we know dx dt. It's -1. So this is just 3/7 times -1, which is -3/7. So this rate here, there's no place to plug in x equals 5. So this is just going to be -1 plus -3/7. Which, let's see, if we get a common denominator, this is -7/7, and a -3/7, that'd be -10/7. And so that's going to be in feet per second, because our units here were feet per second. So it's decreasing, the tip is moving at 10 feet 10/7 feet per second, and it's decreasing because it's negative. So the tip is, the length or the distance of the tip from the pole is decreasing. So you want to try to draw a picture, label it, write down your known, write down what you want, and then write down all the relationships in the problems. So that could be similar triangles, it could be a Pythagorean theorem, it could be a volume or an area formula, and then you've got to differentiate both sides of your equation. Okay, that's important because a lot of people get stuck and they write down relationships and they don't know what to do with them. Well, you have to differentiate them because it's asking about rates, which are derivatives. So you differentiate both sides, you'll get rates in there. And then our other important application was max-min problems, and that's what we've got going on in problem number 6 here. Right triangle has a hypotenuse with length 6, and it's rotated about one of its sides to form a right circular cone. Find the greatest possible volume for this cone, where volume is 1/3 pi r squared h. Okay, so we've got a right triangle here. And the hypotenuse is 6. So there's our right triangle. The hypotenuse is length 6. And it's rotated around one of its sides. Okay, so let's say it's rotated around this side. So then this tip here gets rotated around in a circle like this. And that's going to form a cone. And what we want to know is what's the cone of the greatest possible volume, where volume is 1/3 pi r squared h. Okay, well, let's label on our picture. Here, this is your radius, r is radius, and this is the height of the cone. We've got it tipped on its side. If you want, you could have rotated the other way. And, you know, actually that might be a better picture if we do that. So let's say our right triangle looks like this. And let's rotate it around the vertical side. So then this point is going to rotate around like this. So now here's your radius and here's your height. So either way, it's just whether the cone is right side up or whether it's tipped over on its side. But radius is the distance from the center out. Height is distance from the center of the base to the apex, to the point there. So we know that this side is 6. So let's write down our relationships. So, well, we got a Pythagorean relationship here. We know that r squared plus h squared is equal to 6 squared. That's going to be a restriction. And we want the greatest possible volume. So we want the max of volume, which equals 1/3 pi times r squared times h. Okay, well, to find a max here, you've got to take a derivative and set it equal to 0 and do a max-min test. Before we can do that, we've got to get it down to one variable. We've got radius and height, two things that are variables in there. But what we know is that r squared is the same as, or r squared plus h squared is 6 squared. So if we take this h squared and bring it over here on the right as a negative, then we are going to get that r squared is the same as 6 squared is 36 minus h squared. So now we can get this down to one variable. This will be 1/3 pi, and then in place of r squared we're going to put 36 minus h squared. And then times our h on the end. And why don't we go ahead and multiply this in times each piece. So this is going to be a 1/3 pi times 36h minus h cubed. So now we've got one variable here. And then what are the restrictions on h? So we want to maximize this volume here, which is now all in terms of one variable. And it's going to be on the interval from, well, let's see, our height could be at the smallest, height 0, and it can't get any bigger than 6 because the leg of the hypotenuse, or the leg of the right triangle, can't get bigger than the hypotenuse. So this would be on the interval 0, 6. So now what do we do? Well, now we take a derivative. So now v prime, this is derivative with respect to h, is going to be, I'll write this out, this is derivative with respect to h of our 1/3 pi times 36 minus h cubed. So now the 1/3 pi is a constant. That factors out of derivatives. So this is 1/3 pi out in front times the derivative with respect to h of 36h, oops, I forgot the h right here, minus h squared cubed. And if you don't like h, you can use x in there, that's fine. And this will be a derivative with x. So we got a 1/3 pi out in front. The derivative of 36h is going to be 36. And then the derivative of h cubed is 3h squared. Okay. And now we want to factor greatest common factor out of here and set it equal 0. So this is going to equal, we'll have a 1/3 pi. Let's see, 3 goes into 36. We can factor a 3 out of there. 3 goes into 36 12 times. minus, factor the 3 out of here, h squared is left. And these 3's would cancel. So our derivative is pi times 12 minus h squared. And then you set your derivative equal to 0. Now pi is never equal to 0 because that's just a constant number, so that would mean that the 12 minus h squared is equal to 0. So bring the h squared over as a positive, 12 equals h squared, and then take square roots of both sides. So we get h is going to equal square root of 12. Actually positive and negative, but the positive one is the only one that makes sense. Now square root of 12, 3 squared is 9, and 4 squared is 16. So this is 3 point something, so that is in the right interval. So now we do our max-min test with v prime and v. We want to make sure that this is maximum volume. 0 is the smallest that the height can be, 6 is the largest, and the square root of 12 is here in the middle. And if you figure square root of 12 out on your calculator, this is approximately 3.46. So this is approximately 3.46. So for a test value less than root 12, we could use 3. For a test value greater, we could use 4. And if you plug 3 into v prime right here, 12 minus 3 squared be 12 minus 9. That's positive. So this is v is increasing. Plug a 4 in, 12 minus 4 squared, 12 minus 16, that's negative. V is decreasing. So this is indeed a max. And then what do they ask us? Find the greatest possible volume. So we want the value for volume. So then the max volume is going to equal the volume at square root of 12. Okay. So what we're doing is we are plugging square root of 12 back into our original volume function, but we can plug it in here or here, whichever place. So I'm writing this as v of h, v parentheses h, because volume depends on h. I'm writing it in function notation. So what do we do? Well, this is going to be 1/3 pi, and then 36 times square root of 12 minus root 12 cubed. And then if you want from there, you can plug into a calculator. But this is an exact answer. It's not simplified, but it is an exact answer. And then the partial credit problem here, find the dimensions of the rectangle with greatest area with fixed perimeter of 10. So let's see here. So we want to, if we sketch that rectangle here, let's do length x and width y. So we want to maximize area, which is x times y. And it's going to be subject to the restriction that the perimeter, the distance around, that's going to be 2x, because this is x and this is y. 2x and 2y is equal to 10. So 2x plus 2y equals 10. And here if you divide both sides by 2, everything, you get x plus y equals 5. So then we want to get this function down to one variable. So your area is equal to xy, which if we bring the x over as a negative here, y will equal 5 minus x. So plug that in here. So you got x times 5 minus x. And now multiply your x in. We'll have 5x minus x squared. And so there's our function a. And that's going to be on the interval, the smallest x could be is 0, and the biggest the x could be is, well, the whole perimeter is 10, so the biggest this could be is 5 and 5. So it's on the interval from 0 to 5. So if you get any critical numbers that are outside that interval, you ignore them. So then a prime is going to be the derivative of this function. So that's going to be 5 minus 2x. And then set that equals 0. Bring the 2x over as a positive. 5 equals 2x. And then divide both sides by 2. So x equals 5 halves. Or 2.5. And then if you do a little max-min test here, 5 halves is right in the middle there. So you can look at your A prime up here and your area down here. So let's test 1 and 4. So if you take 1 and plug into A prime here, 5 minus 2 times 1, positive. Take a 4, plug in, 5 minus 2 times 4, that'd be negative. So this is increasing, decreasing, that is a max. And here they ask us find the dimensions. So x is 5 halves, and then your y is going to be 5 minus x. So 5 minus 5 halves. If you get an LCD, that's 10 halves minus 5 halves, which is 5 halves again. So those are our dimensions, 2 dimensions. So again, I'd recommend looking over some of the other max-min problems. There's only a finite number of types of max-min problems, but you've got to write down your relationships, get it to one variable, and then you got to take a derivative again. Okay, you can't solve a related rate or a max-min without taking a derivative. Okay, number 7, we're performing some integrals here. Both of these involve u substitutions. This one's a little easier. Let's take a look at that one first. So actually, I mean, if you wanted to, the long way to do this would be 4 minus x squared times itself 3 times, but see, the derivative of x squared is 2x, and we've got the x out here. Okay, so I think we want to let use a u substitution and let u equal 4 minus x squared. And then your du is going to be derivative 4, 0, derivative of negative x squared is negative 2x dx. And then, let's see, we've got the x out here. We need a negative 2, so let's multiply by negative 2 on the inside. Needed a little bit more room there. Okay, so we need a negative 2 in here, and then negative 1/2 on the outside. So all I did was multiply by 1. So these two together make up my du. So this is now going to be negative 1/2 on the outside, and then integral, this is u, it gets cubed, and the rest of the integral is du. So this is just u cubed du. But this is a definite integral, so we got to take the 0 and the 1 and plug them in here for x. So x equals 0 gives us u equals 4 minus 0 squared, so 4. So this is a 4. And then upper limit, x equal 1. X equals 1 is going to give us 4 minus 1 squared. 4 minus 1, 3. So this goes from 4 to 3. Whoops. Said 3, wrote 4. There we go. So this is now just power rule. So this is u to the 4th. Whoops, don't forget our negative 1/2 out in front. Negative 1/2, and then this is u to the 4th divided by 4, and that gets evaluated from 4 to 3. So you plug in the top number, plug in the bottom number, and you subtract the bottom from the top. So this is going to be a negative 1/2 out in front. And then plug in the 3. We're going to get 3 to the 4th over 4. minus plug in the 4 to the 4th over 4. And then you can do the calculator work from there if you want. And you get a final answer of 175 eighths. Okay, because that's going to end up being our common denominator. Okay, so this ends up being 175 eighths. Just plug it in the calculator. Now let's try this guy. So let me copy that down. So at first, you look at this and I see the 1 over x and you're like, oh, okay, well, gosh, you know, like x squared here, derivative of x squared is 2x, and here the x is on the bottom. But remember, u is almost always an inside function here. So see, if we let our u equal 1 over x, then this would be sine of u on the top, which is going to make that integral significantly easier to evaluate. So why don't we try that? So in here, let's let our u equal 1 over x, which if we want to differentiate that, that's going to be x to the negative 1 power. So bring it up with a negative exponent. So then your du, negative 1 comes down, times x, and decrease your exponent, negative 2 power, which is negative 1 over x squared, and then times dx. Well, here we've got dx on the top, we've got x squared on the bottom, and if you want, put the 1 out here in front. So we've got 1 over x squared, we need negative 1 over x squared. So let's multiply by negative 1 on the inside and negative 1 on the outside. So now we've got a negative 1 on the outside, negative 1 dx, or negative 1 over x squared dx, that's our du. So this will now be integral du, and this is sine of u. And then we need our limits of integration changed over. So we've got to plug in 4 over pi. So here, if x equals 4 over pi, then our u here is 1 over x. It's the reciprocal. So u is going to be pi over 4. That's 1 over 4 over pi. It's just reciprocal. So this is going to be pi over 4. And then same thing here. If you plug 2 over pi in for x here, you're going to get pi over 2, the reciprocal. And we know how to do the antiderivative of sine. That's negative cosine. So you got this negative 1 on the outside. Antiderivative of sine is negative cosine of x. And then we are evaluating from pi over 4 to pi over 2. And these two negatives are going to make that a positive cosine x. So we just want, let me erase this guy here. Do 175 eighths there. So plug in pi over 2, plug in pi over 4 and subtract. So this is going to be cosine of pi over 2 minus cosine pi over 4. Remember, the cosine of pi over 2, the x-coordinate on unit circle is 0. And cosine pi over 4, that's the root 2 over 2. That unit circle might be a little rusty. You might want to get that out. So that's an exact answer. Negative root 2 over 2. And then the last two questions are the chapter 5. Find the area of the region enclosed or trapped between x cubed and 8x. So if we graph this guy, y equal x cubed comes up like this. And then y equals 8x, that's y equal x cubed. And then the y equal 8x is a line. It's going to come up like this. and we want the enclosed area. So we want these two pieces. But by symmetry, they're equal to each other. Well, let's first find the intersection points. So we've got to set our x cubed equal to 8x. Bring this over as a negative. X cubed minus 8x is equal 0. Factor a common x out. X squared's left here, and negative 8 is left there. So either the x equals 0 or the x squared minus 8 equals 0. If we bring the 8 over, that would mean x squared equals 8, and take square roots here. X is going to be plus or minus square root of 8. So it didn't get nice cutoffs there, but this one is square root of 8, and this one is negative root 8, and then of course here this is the origin. So if we call this area 1 and this guy area 2, then we know that area 1 equals area 2, and so our total area here is going to equal 2 times area 2. So we'll just find 2 times area 2. So 2, and then area 2 is just going to be the integral of top function minus bottom function. So this is going to be integral of the top function is the 8x, and the bottom function is the x cubed. And that's with respect to x, so that's top minus bottom, and we're adding those up from 0 to root 8. Remember, we're adding up rectangles, vertical rectangles, their areas. This is base and this is height. And then this is not a hard integral to do. This is just power rules. So you got that 2 out in front, and let's see, this is going to be 8 times x squared over 2 minus increase the exponent divided by the new exponent, x to the 4th over 4. And that goes from 0 to square root of 8. So you got a 2 here. 2 cancels into the 8, leaves a 4. So if we plug in the square root of 8, this is going to be 4 times root 8, and that gets squared, which is just going to be root of 64, or 8. The square and the square root cancel. Minus root 8 to the 4th power over 4. So we've got that 2 out in front. This is 4 times 8, 32, minus root 8 to the 4th power. Well, root 8 times root 8 is 8. That would be 2 of the root 8s, and another 2 root 8s is going to be another 8. So this is 64, and divide by 4 is going to leave 16. And you can do that on a calculator if you want to. And so 32 and a 16 is 16 times 2 is 32. Okay, so total area is 32. This would be 16 here and 16 here. Remember, area enclosed between the curves, it does not treat area below the axis as negative. So here's one where we integrated with respect to x. Let's look at another one. Find the area between y equal x squared plus 2 and y equal 1 minus x from 0 to 2. Okay, so y equals x squared plus 2, that's the x squared curve shifted up 2 units, like this. Okay, so that's that guy there. And then y equals 1 minus x. So y-intercept is 1, your slope is negative 1, so fall 1, run 1, right there. So that's going to be this line. And then we are doing between 0 and 2. So x equals 0 would start here, and x equals 2, we would end here. Whoops. Just use my line tool here. There. So we want that area right there, and including that piece. So let's see here. We want to do vertical rectangles on this one here because all the way across we've got a consistent top function and a bottom function. This is the line y equal 1 minus x. And that's the bottom function. The top is going to be the x squared plus 2. So our area here is going to be the integral from, we're adding up rectangles from x equals 0 to x equal 2. This is at 2. So 0 to 2. Top function is the x squared plus 2. And minus the bottom function is the 1 minus x. Make sure you put those parentheses in there because you're subtracting off that whole function. So now let's simplify, take out our parentheses here. So this is going to be -1 and a positive x. So this will be x squared plus x, positive 2 and -1 plus 1. And this is just power rule. So increase your exponent, divide by the new exponent. So x cubed over 3 plus integral of x is x squared over 2. And antiderivative of 1 is x. And we are evaluating from 0 to 2. So, back here, I plugged the root 8 in. I didn't plug the 0 in because 0 squared and 0 fourth are both 0, so that doesn't contribute anything. Same thing happens here. We plug in the 2, we're going to get values in each one. But we plug in the 0, 0 cubed, 0 squared, 0. The 0 doesn't contribute anything. So plug in the 2. 2 cubed is going to be 8 thirds. Plus, plug in the 2 here. 2 squared is going to be 4 halves. And then plus, plug in the 2 here, 2. And let's see, 2 goes into 4 twice. So this is 4 plus 8 thirds. 2 and 2 here is 4 and 8 thirds. So we need a common denominator. You'd multiply top and bottom by 3. So 12 thirds plus 8 thirds, 20 thirds is our area there. And then finally, we are ending up with a solid of revolution. We're revolving the region between y equal root x and x squared around the x-axis. Okay, so y equal x squared looks like this. And then square root of x looks like this. And so here's the region enclosed. We're revolving that around the x-axis. So that's going to look like this and this. And we're revolving it around like this. So we get this bowl with a caved-in funnel taken out of the inside. We want the volume of that. So remember what you do is here we're either using discs or washers here, and you pick a general X here and then sketch what a general washer would look like. Look like that. So here you've got an outer radius and an inner radius. So right here your outer radius is on the function root x, and then in here your inner radius across here, and it's radius from the x-axis. Your inner radius is going to be touching on y equal x squared, so inner radius is x squared. So remember our volume here is the integral from a to b of pi r squared, but we've got 2 radii, so this is going to be our outer squared minus our inner squared, and with respect to x. So our intersection points here are going to be where x squared equals root x, set the two equations equal. Square both sides here. So x squared squared is x to the fourth. Square root and square undo each other, that's x. So x to the fourth minus x is equal to 0. We can factor out an x here. X cubed's left here, and then minus 1 there. So either the x equals 0, or x cubed minus 1 is equal 0, in which case we can add 1 to both sides and get x cubed equals 1, and then take cubed roots, x equals 1. So this is happening at x equal 1, and this intersection is at x equals 0. Okay, so this down here is at x equal 1, and that is 0. So we are going to be doing an integral from 0 to 1 of pi, and we already decided that our outer radius was the root x, so root x squared, minus our inner radius was x squared, for that disk that was at x, and then the integral is going to add these up from 0 to 1. So let's see, our pi can come out of the integral, so pi on the outside, integral is 0 to 1. Root x squared, the square and square root are going to cancel each other here, we're just going to get x. Power to a power, multiply, so minus x to the fourth. And now this is just power rule. Do the antiderivative here. So pi times, this will be x squared over 2. Increase the exponent, divide by the new exponent. Minus x to the fifth over 5. And that's going from 0 to 1. So we plug in a 1 here and here. This is going to be pi times 1/2 minus 1/5. And then if we plug in 0, 0 squared, 0 to the fifth, that's 0. That's not going to contribute anything. So 1/2 minus 1/5 times pi. So if you get a common denominator here, this is 5/10 and this is 2/10. So 5/10 minus 2/10, this is 3/10 pi. But you have an exact answer here. It's just not simplified, and you're not required to simplify. So remember to go back and review your, at least your hour test, and hopefully your hour test and practice exams for the limits and for the derivatives, and then also for the integrals, because those can vary quite a bit. And then be helpful to look at some different related rate problems and some max-min problems. Those are the ones that can probably vary the most.